Okay, I am going to give a basic introduction to the definitions of Galois connections. Usually we talk about first of all, Galois connections is a kind of relationship between two partially ordered sets. Okay. And yes, here I'm using this symbol for partial order. I could use this one, but I just don't feel like it. Okay. So, usually we talk about monotone Galois connections, but the antitone Galois connections are actually more symmetric. So, in some ways, they are simpler. In a Galois connection, we will have an antitone function from P to Q, and then another from Q to P. And there are two antitone functions that will be adjunct or joint. Okay, there's two big definitions that are equivalent. Okay, the two main ones, the two most important. Definition 1. Okay. So let's be more clear. Given two partial orders alpha from P to Q and beta from Q to P form Galois, let's be clear, an antitone Galois connection if definition. Okay, I'll explain. So definition 1. For sorry, let's be clear. So what's going to be the Galois connection? Alpha beta will be a Galois connection if, okay, and then a definition. Okay, definition 1. This is where we have, let's say, the Galois relation, where for any P in P and Q in Q, we'll have that P smaller than am I correct? Sorry, no. Q smaller than alpha P is equivalent to P smaller than beta Q. Okay. So we can swap P and Q. This is one definition, which maybe is a bit weird because they swap around. And then the second definition, which is equivalent, is alpha and beta are isotone. First, there must be two properties: are isotone, and alpha and beta are both I don't know what the name is, but let's say inflationary. inflationary. Okay. That is, so let's re-explain definition 1, definition 2. First property is for any P and P smaller than P prime implies alpha P is greater than alpha P prime. Okay, so it inverts the sign. And property 2 is for, so this is going to be true for alpha, and then we will say the same for beta, by the way. So alpha is isotone and beta is isotone as well, same thing. And then the second property, alpha, will be inflationary. That is, we will have that for any P. Oh, I fucked up. Whatever, it's fine. Alpha compose beta and beta compose alpha are inflationary. Okay. What does that mean? It means for any P, alpha, beta, alpha composed beta of P will be, let's move it will be greater than P. Okay, and then we're gonna have the same thing for all Q, Q, beta, alpha, Q. Okay, also I made a mistake. You see here, this shouldn't be P, this should actually be Q, because the domain of alpha is Q. Okay, very confusing video, but I'm practicing. So yeah, these are the two equivalent definitions. Definition 2, definition 2 again, and definition 1, where I just did the second definition 2 to explain the terms used. These terms, isotone, inflationary. I don't know if inflationary exists, but I don't know what the actual name that you would use is. I've seen extensive words. But anyway, okay, let's prove it. Proof that D1 is equivalent to D2. Okay, let's do the sufficient part. Definition 1 is sufficient for definition 2. Okay, we don't have any, like, this basically only ever lets us get inequalities from other inequalities, pretty much. So the only one that, the only inequality we can start with that we know for sure is that P is smaller than P. And by smaller I mean smaller or equal, but I prefer writing it this way. So P is smaller than P, that's always true for any partial order whatsoever. Okay. And this is going to tell us by an application of this, no. Well, this is true, but we have to remember that we want to apply this definition, so we need alpha to be present, or beta. Okay, therefore we always know that P beta P is smaller than beta P. Therefore P is smaller than alpha P, alpha beta of P. Okay, by an application of the Galois relation. Correct? Is this correct, or did I mess up? So what happens is that, like, our beta will transform into an alpha, and the arguments switch place. Okay, so we're gonna switch it. Yeah, so this switch place, okay, and limit beta became an alpha. Okay, it's all correct. So here we prove that definition 1 implies the second property of the definition 2. Then let's prove that it implies the first property. Okay, so for any, and obviously as a result this is also proved for so we proved it for the P, and we proved for alpha composed beta, but obviously the same result will follow for beta composed alpha. Sorry, for Q we will know that beta composed with alpha, Q, is also greater than Q. It's very easy to prove. Okay, it's just the same thing. Now we just do the same again. Let's prove that definition of 1 implies the property 1 of definition 2. Now this is useful. Remember that we have P, alpha, beta, P. We know this is true. Okay, but our starting point in the property 1 is for all Q and Q prime, we have that Q smaller than Q prime. But now we want to get an alpha here somehow. Okay, there's a way to get an alpha. Okay, we just insert the alpha here, because we know this is going to imply, trivially this is true, so it implies this, but greater than the Q is beta alpha Q. Let's remove the non-important part, and we get beta alpha Q. Okay, this is not multiplication, just composition. Okay, and from this we get alpha Q, alpha Q. Okay, now we proved that the first property of definition 2 for Q, but obviously for P and P prime we give the same argument, and we will have proof it for both Q and P. So for both beta composed alpha and alpha composed beta will be inflationary. Here we proved that beta composed alpha is inflationary. The other proof is the exact same thing. Okay, so definition 1 implies definition 2. It's done. Now let's prove that definition 2 implies definition 1. Now, just as a reminder, these are definitions. We want to prove that if alpha and beta are isotone, and alpha composed beta and beta composed alpha are inflationary, then we have the Galois relationship here. Okay, let's just remind ourselves, if alpha and beta are isotone and alpha beta and beta alpha are inflationary, we have that. Then this is not strictly the same as a then, but I'll just say it like that. Then we have So if we have this, then alpha beta and beta alpha. Sorry, no. We have the Galois relation. Okay. Now proof. Should be easy, right? Let's think. Okay, let's say that Pew again. Okay, P is smaller than, beta P, right? Is it beta or alpha? Let's check. There we are. It's alpha P. Sorry, Q is smaller than alpha P. Then what can we do? Then we get that we can apply beta here. Then beta Q is greater than beta alpha P. And we know this one. You see, beta alpha, we can reduce this. We know that this is greater than P. And so we just prove that beta Q is greater than P. Now, the other proof is equivalent. We just have to do the same thing. Let's start with this. I'll just keep going. So if we have beta Q is greater than P, here we can just apply alpha beta Q alpha P. Sorry, it's antitone. And this implies, let's separate the weekly. And this implies we see a key here, alpha beta, which so we always know that we can reduce this. So Q, alpha beta Q, smaller than alpha P. Okay, so Q smaller than alpha P. Ooh, okay, that's done. So we have Antitone Galois Connections. We have definition 1, that, and we have two partial orders, P and Q, alpha and beta, and we have two definitions of alpha, beta form an antitone Galois connection. Let's say it like this. Okay, the first connection basically just says that we have a Galois relation where we can change the alpha to a beta, and we prove that this is equivalent to definition 2, where we have both antitonicity and we have inflation. Okay, that was an experience. These are equivalent. Why does it matter? Well, I didn't say why it matters, but I think it does.